Welcome to Lecture 24, in which we will talk about quantum teleportation. And so the idea of this problem is that Alice has a qubit whose state phi is equal to A0 plus B1, where Alice does not know the values of A and B. So she has this unknown state, and she would like to enable Bob to construct this state as a result of her sending to him 2 classical bits. So the way that this goes is as follows. The first step is just like what we have in dense coding, the entangled pair, which we will call C0, which is 1 over square root of 2 0, 0 plus 1, 1, is distributed to Alice and Bob so that Alice possesses the first qubit and Bob possesses the second. So if we take into account this entangled pair plus the state, the unknown state phi that Alice has, then the starting state for this problem is the tensor product of phi with C0. So we have the tensor product of A0 plus B1 with 1 over square root of 2, 0, 0 plus 1, 1. And so let's go ahead and calculate what this will be. We can pull out 1 over square root of 2 in the front, and this would give us A times 0, 0, 0 plus 0, 1, 1 plus B times 1, 0, 0 plus 1, 1, 1. Now, again, this is the starting state for this problem. Now, what Alice will do is essentially the reverse of what Bob does in the dense coding problem. In other words, she first applies, and keep in mind that Alice controls the first 2 qubits, and because she has the unknown state, and then she has the first qubit of the entangled pair. So Alice has the first 2 qubits, and Bob has the last one at this point. And so what Alice is going to do is first apply the C0 gate. So Alice first applies a C0 gate to her two qubits. Now, when she does this, let's see what the final result will be. Okay, we'll just bring down the 1 over square root of 2 and the A. And when she applies the C0 gate to the first 2 qubits of 0, 0, since the first qubit is 0, the second qubit will remain the same. So 0, 0, 0 will remain 0, 0, 0. When she applies the C0 gate to the first 2 qubits here, again, those will remain the same because the first qubit is 0, and therefore the second qubit does not get changed. So plus 0, 1, 1. Now for the next part, when she applies the C0 gate to the 1, 0, 0 ket, since the first qubit of that is 1, the second qubit is going to get flipped, and that will give 1, 1, 0. And likewise, when she applies the C0 gate to the first two qubits of the 1, 1, 1 ket, she will get 1, 0. So we'll have 1, 0, 1 here. So that's what the result is at the end of Alice applying the C0 gate. Now, if you will recall from the dense coding problem, after Bob applied the C0 gate, then he applied the Hadamard gate to the first qubit. And so we will do this, Alice is going to do this as well. So now Alice applies the Hadamard gate to the first qubit. Well, let's just say she applies it to the first qubit. The result is, and by the way, before I go any further, the problem for this lecture is going to concern what would happen if everything went in exactly the same way that I'm describing now, except for the very first step. Instead of applying a C0 gate, we'll have Alice apply some other transformation, and we'll talk about that when we get to the problems. But everything else will be the same. Okay. So now, after applying the C0 gate to the first two qubits, then Alice applies the Hadamard gate, and this time only to the first qubit. And so what will the result be this time? Well, we'll have 1 over square root of 2, and then we'll bring down the A. And remember that when we apply the Hadamard gate, the way that it acts on a single qubit is that the Hadamard gate acting on 0 will give the plus ket, which is 1 over square root of 2, 0, plus 1 over square root of 2, 1. And the Hadamard gate acting on the 1 ket will give 1 over square root of 2, 0, minus 1 over square root of 2, 1, or the minus ket. So when we apply the Hadamard gate to the first qubit here, we will get 1 over square root of 2, 0, 0, 0, plus 1 over square root of 2, 1, 0, 0. And then when we apply the Hadamard gate to the first qubit in this ket, we will get plus 1 over square root of 2, 0, 1, 1, plus 1 over square root of 2, 1, 1, 1. Now let's see what happens to the rest of this. When we apply the Hadamard gate to the first qubit of the 1, 1, 0 ket, well, the Hadamard gate acting on 1 is 1 over square root of 2, 0, minus 1 over square root of 2, 1. So we will get 1 over square root of 2, 0, 1, 0, minus 1 over square root of 2, 1, 1, 0. And likewise, when we apply the Hadamard gate to the first qubit here, we'll get plus 1 over square root of 2, 0, 0, 1, minus 1 over square root of 2, 1, 0, 1. And that is the result after that step. And now let's observe that this can be written as, okay, everything inside the brackets has a 1 over square root of 2 multiplying it. So we can take all those 1 over square root of 2's out and combine it with the 1 over square root of 2 that we already have to give us a 1/2 outside the brackets. And now we will have a times 0, 0, 0 plus 1, 0, 0 plus 0, 1, 1 plus 1, 1, 1 plus b times 0, 1, 0 minus 1, 1, 0 plus 0, 0, 1 minus 1, 0, 1. And now let's make one more observation. If we can rewrite all of this in the following way. This first term, 0, 0, 0, a times 0, 0, 0, and then this seventh term, b times 0, 0, 1, could be joined together to give us 0, 0 tensor product a0 plus b1. Again, that's the first term and the seventh term. Now we could have 0, 1 tensor product with a1 plus b, and let's see, 0, 1 is 0. And that is resulting from the combination of the third term in the brackets with the fifth term in the brackets. Both of those start with 0, 1, and what's left over is a times 1 plus b times 0. Then if we try to take out 1, 0, we'll have a 0 here from the second term, and minus b1 from the eighth term. So again, now let's just review. The first term came from term 1. I'll number the terms. 1, 2, 3, 4, 5, 6, 7, and 8. And so this first parenthetical term comes from terms 1 and 7. The second parenthetical term here comes, we have from 3 and 5. Now for the third parenthetical term, we have 2 and 8, and then finally this final term comes from terms 4 and 6. So if you look, we have terms 1, 2, 3, 4, 5, 6, 7, and 8. So we haven't used any terms more than once, and we have used all the terms from above. So this expression is equal to what we have here. And now we see that if Alice, now again remember that Alice is controlling only the first 2 qubits. And so now she can make a measurement with the standard basis, and in other words with the basis 0, 0, 0, 1, 1, 0, and 1, 1, and she will get one of these parenthetical terms for sure. The probability for each one is 1/4. It's 1/2 squared. So there's a 1/4 probability that Alice, when she measures, will obtain this. A 1/4. Well, excuse me. Let's phrase that a different way here. Okay, let's say it this way. Alice, when she measures with the standard basis, she will either obtain 0, 0, or 0, 1, or 1, 0, or 1, 1. She's going to obtain, certainly, of course, as always is the case, when you measure with any basis, you're going to obtain one of your basis vectors, or basis states. And so she's going to measure one of these, and she will measure each one of those with a probability of 1/4. But which one she measures, she is then going to send the result to Bob, send the resulting state. After she measures the first 2 qubits of the state, she will send the resulting state to Bob. And so if she measures 0, 0, then Bob is going to be getting this. If she measures 0, 1, Bob will be getting this. If she measures 1, 0, Bob will be getting this. And if she measures 1, 1, Bob will be getting this. So how do we finish up this problem? How does Bob reconstruct the unknown state phi that Alice started with? Okay, I'm sorry, let me say this one last time. Okay, so Alice is going to measure the first 2 qubits in the standard basis. And when Alice measures the first 2 qubits with the standard basis, and just to remind you, that's 0, 0, 0, 1, 1, 0, 1, 1. She will obtain one of these results. One of these as her result. The probability of each is 1/4. Okay? If she measures 0, 0, then Bob's qubit, remember Bob has only the last qubit. Alice had the first 2 qubits, Bob has the last one. But if she measures 0, 0, then Bob's cubit must be A0 plus B1. If she measures 0, 1, then Bob's cubit must be A1 plus B0. If she measures 1, 0, then Bob's cubit must be A0 minus B1. And finally, if she measures 1, 1, then Bob's cubit must be A1 minus B0. So, how does Alice enable Bob to create the unknown state phi, which I will remind you was equal to A0 plus B1? Well, the answer is this. She sends to Bob two classical bits as follows. Okay? If Alice measures and of course, again, there's 4 different things that Alice could measure: 0, 0, 0, 1, 1, 0, and 1, 1. Okay. She sends the 2 classical bits, and she'll just send 0, 0, 0, 1, 1, 0, 1, 1. So she'll send these 2 classical bits to Bob, and then Bob will apply to his qubit I X Z Y. His result will be okay. So let's look above and we can finish up this problem. Okay, if Alice measures 0, 0, that means that Bob's state was A0 plus B1. And if he applies the identity transformation to A0 plus B1, he will get A0 plus B1. On the other hand, if Alice measures a 0, 1, that means that Bob's qubit is A1 plus B0. And so, but in that case, if Alice measures a 0, 1, she's going to send 0, 1 to Bob, and then he knows to apply the X transformation, which, remember, sends 0 to 1 and 1 to 0, so this will become A0 plus B1. On the other hand, if Alice measures 1, 0, that means that Bob's qubit is A0 minus B1. And what will happen then is that Alice will send a 1 and a 0 to Bob, those 2 classical bits. and whenever he gets a 1 and a 0, he will apply the Z transformation, which maps 0 to 0 and 1 to -1. And so the A0 stays as A0, but the minus B1 becomes plus B1. And so then, Bob, the result would be A0 plus B1. And finally, if Alice measures 1, 1, that means that Bob's qubit is A1 minus B0, and she will send to him, in that case, the two classical bits 1 and 1, which will tell him to apply the transformation Y. And remember that the transformation Y sends 0 to -1 and 1 to 0, so this will become A0 plus B1. So in every single circumstance, even though Alice, remember, she never knows what A and B are equal to, but she does know what she measured, and she can send those two classical bits to Bob, and then that will tell him what transformation to apply to his qubit to obtain the unknown state phi. And so that is quantum teleportation, because the unknown state phi, which originally belonged to Alice, has, as a result of her doing some transformations and then sending two classical bits, Bob has now been able to recreate that state, as we can see here. And so that's quantum teleportation. And now the problem, well, let's discuss the problems. Okay, so now we'll talk about the problems, and I've already hinted a little bit about what you needed to do, but let's talk about it in more detail now. So there are going to be 4 problems here that are all related to this same situation. What we're going to do is we're going to suppose just one change in the quantum teleportation algorithm. In this very first step, let's scroll back up. Remember that in the very first thing that Alice does, I mean, here we have identified the starting state. The starting state can be written like this. And the very first thing that Alice does is to apply a C0 gate to her 2 qubits. Remember, Alice has control only over the first 2 qubits. And the first thing she does is to apply a C0 gate to those 2 qubits. Then she applies a Hadamard gate to the first qubit. Then she measures with the standard basis, and then she will send Bob either a 0 and a 0, a 0 or and a 1, a 1 and a 0, or a 1 and a 1. So that's what Alice does. Now in this problem, we are suggesting just one change, and it's at the very first step. Instead of applying the C0 gate to her 2 qubits, she will apply this M transformation. Now the M transformation is given as a matrix here, and this is the matrix of that transformation relative to the standard basis in the standard order. So what that means is that M00, that's in the first column, M00 is 1/2 0 0 plus 1/2 0 1 plus 1/2 1 0 plus 1/2 1 1. M acting on 0 1 is 1/2 0 0 plus 1/2 0 1 minus 1/2 1 0 minus 1/2 1 1. M acting on 1 0 is minus 1/2 0 0 plus 1/2 0 1 plus 1/2 1 0 minus 1/2 1 1. And finally, M acting on 1 1 is 1/2 0 0 minus 1/2 0 1 plus 1/2 1 0 minus 1/2 1 1. So that is what Alice will do. She will apply this transformation to those first 2 qubits of the starting state. After that, she will do everything else just as she did up here. So she'll do that instead of applying the C0 gate, but then everything else will be the same. In other words, she will then apply the Hadamard gate to the first qubit, and then she will send to Bob a 0 and a 0 if she measures the 0, 0 cat, a 0 and a 1 if she measures the 0, 1 cat, a 1 and a 0 if she measures the 1, 0 cat, and a 1 and a 1 if she measures the 1, 1 cat. And so the question here, it says, if Alice conducts the rest of her steps as described in the lecture, what transformation should Bob apply in order to obtain phi equals A0 plus B1 if Alice sends her 0, 0, if Alice sends him 0, 1, if Alice sends him 1, 0, and if Alice sends him 1, 1. You see up here, when Alice sends him 0, 0, he needs to apply the identity transformation. When Alice sends him 0, 1, he needs to apply X. When Alice sends him 1, 0, he needs to apply Z. And when Alice sends him 1, 1, he needs to apply Y. And if he does that, then in each case he will obtain A0 plus B1. We want him in each case to obtain A0 plus B1 here as well, but it's just that, because Alice has done some things differently, now Bob is going to have to apply different transformations in each one of these cases. And so you need to figure out in each case what transformation Bob should apply to his qubit, which of course is the last qubit. You need to figure out what transformation he needs to apply in each of these 4 different cases, so that in every case he will eventually obtain this state A0 plus B1. And so that's it for lecture 24, and good luck.